Have you ever really thought about what makes a lemon so sour? Or what gives a car battery its juice? Well, the answer to both is actually the same thing, a type of chemical we call an acid. So in this explainer, we're going to break down what an acid really is from the inside out.
Okay, so what do lemons, car batteries, and a can of soda all have in common? I mean, on the surface, not much, right? But chemically, they're basically family. They're all connected by this property we call acidity. It's the secret behind that sour taste, that fizzy pop, and even that powerful electrical kick.
So here's what we're going to cover. First, we'll look at the acids you run into every single day. Then, we're going to uncover the one chemical secret that they all share. We'll get into why some acids are way stronger than others, learn the surprisingly simple logic behind their names, and even see how chemists count them up. Let's dive in.
All right, let's kick things off. You know, when you hear the word acid, you probably picture bubbling beakers in some mad scientist lab. But the truth is, they are literally all around us. In your kitchen, in your car, and yeah, even inside your own body.
So what's the deal with all these different acids? What do they have in common? Well, for one, many of them have that distinctive sour taste. You know what I'm talking about. They can also be corrosive, meaning they can eat away at stuff. And here's a cool one. When you dissolve them in water, that solution can conduct electricity, which is exactly how a car battery works. And they're not just liquids. Some acids are actually solid.
Just think about it. You've got citric acid in lemons, ascorbic acid in tomatoes, acetic acid in vinegar. That fizzy bite in your soda? That's carbonic acid. The heavy hitter in a car battery is sulfuric acid. And the stuff digesting your lunch right now? That's hydrochloric acid. They are truly everywhere.
Okay, so we know they're everywhere. But what is the one thing, down at the molecular level, that actually makes something an acid? What's the secret ingredient? Well, turns out it's a lot simpler than you might think.
And here it is, the big secret. Back in 1887, a chemist named Svante Arrhenius just completely cracked the code. He figured out that an acid is simply any substance that, when you drop it in water, releases a very specific little particle, a hydrogen ion, written as H+. That one simple idea changed everything.
Let's see that in action, because it's actually pretty straightforward. Take hydrogen chloride, which is a gas. The moment it hits water, it just splits apart. It breaks up into a hydrogen ion, our H+, and a chloride ion. And that little H+ ion that's now floating free, that's the dead giveaway that you've got an acid on your hands.
Okay, hold on. If the big secret is releasing a hydrogen ion, you might be thinking, does that mean any old molecule with hydrogen in it is automatically an acid?
Nope, not even close. And this is a really important point. Just look at methane gas or glucose, which is sugar. They are loaded with hydrogen atoms. But when you put them in water, those hydrogens just stay put. They don't break off as H+ ions. So you see, the key isn't just having hydrogen. It's the ability to let it go when it's in water.
So, all acids are hydrogen ion donors. We've got that down. But here's the thing. They are not all created equal. Some are super generous with their ions, while others are, well, a little more stingy. And that is the crucial difference between a strong acid and a weak one.
This picture really says it all. Look at the beaker on the left. That's a strong acid. It has completely broken apart. Like 100% of the molecules have thrown their hydrogen ion into the water. But now look at the weak acid on the right. It's much more reserved. Only a few of the molecules have split up, while most of them are still hanging together.
And you'll definitely recognize some of these names. In the strong acid column, you've got the heavy hitters like hydrochloric acid and sulfuric acid. Then, over in the weak acid camp, you find more of the everyday stuff. Carbonic acid, which makes your soda fizzy, and acetic acid, which you know is plain old vinegar.
And get this is wild. One of the most powerful acids on that strong list, hydrochloric acid, is the exact same stuff that's in your stomach right now, helping you digest food. Isn't that incredible? Our bodies are amazing little chemical factories.
All right, so with all these different acids running around, how in the world do chemists keep them all straight? Well, it's not just random, I promise. There's actually a surprisingly simple system for how they get their names.
For the really simple acids, the ones with just two elements, like hydrogen and something else, the rule is super easy. You start with the prefix hydro, then you add the root name of that second element, and you finish it with ic acid. So HCl becomes hydrochloric acid. See? Simple.
Now things get a little more interesting when oxygen jumps into the mix. For these, the name all depends on how many oxygen atoms there are. The one with more oxygen atoms gets an isic ending,
like in sulfuric acid. The one with fewer oxygen atoms gets an us ending, making it sulfurous acid. Just remember, more oxygen is isic, less oxygen is us.
Okay, there's just one last way chemists sort these things, and it's basically just a counting game. It all comes down to a simple question. How many hydrogen ions can a single molecule of the acid actually donate?
First up, you've got the monoprotic acids. And mono, you guessed it, means one. A molecule like hydrochloric acid can give away just one single hydrogen ion. That's it.
Next up are the diprotic acids. Di, of course, means two. Sulfuric acid is a classic example here. Each molecule has two hydrogen ions it can release into the water.
And I think you know where this is going. We finish with triprotic acids, with tri meaning three. Phosphoric acid is a great example, capable of donating a grand total of 3 hydrogen ions from each molecule.
So let's just put it all together in one place. It's pretty clear, right? Monoprotic acids like HCl give up one H+ ion. Diprotic acids like sulfuric acid give up 2, and the triprotic acids like phosphoric acid can donate 3. It's all about how many of those all-important hydrogen ions they have to give.
So there you have it. The secret identity of every single acid is its power to release that hydrogen ion. That tiny H+ particle is the source of everything that makes an acid an acid. But this brings up one last really interesting question. What in the world happens when this powerful little ion meets its total chemical opposite? Well, that's a story for another explainer.